And this is my portfolio for CSCI 3333 programming languages. In this collection, we'll explore key topics in programming languages such as theories and implementations through a mixture of Python programming and grammar analysis. First, we'll start off with Python higher order functions and list comprehensions. Second will be ambiguous grammars. Third will be infix to postfix conversions. And then fourth will be bottom up parsing. Each section will have an example and demonstration. So first, let's discuss the perfect number. A perfect number is a number that equals the sum of its proper divisors. For example, 28 has divisors of 1, 2, 4, 7, and 14. Add them up, you get a total of 28. So that's perfect. All right, so here's how this code works. From functional tools, we import reduce. We import reduce, which helps us combine values into one result. And then, as you see in the code, we define as a perfect number. We list the potential factors, open bracket, I for I, and range within parentheses, 1 comma num, close parentheses, and then close that bracket. This gets all numbers less than num. All right, so factors equal open bracket, x for x, and potential underscore factors if num percentage x equals 0, close brackets. This filters out only the divisors. And then on that next line of code, we'll do the sum underscore of factors equals reduce, and then everything listed right there in parentheses. We use reduce to sum the factors, and then finally return sum of factors in the number. We return true if a number is perfect. So we test the case. If it's perfect, it'll return true. If it returns 6, it'll be true. And then if it returns a number such as 12, it's going to be considered false. And that's how you check for perfect numbers in Python. Next up, we have ambiguous grammar. So a grammar is ambiguous if we can generate the same string using more than one distinct structure or parse tree. All right, so we look at our grammar rules, and using this example, we'll use a string AB to demonstrate ambiguity. Excuse my pronunciation on that. So considering we start with method 1, right? So first step is start with S to SS. First S becomes ASB with S as empty. And then we notice that the caret that usually symbolizes an exponent, we're going to use that as empty. So giving BA, and then the last step in method 1, we're going to combine them. So AB plus BA will equal AB. Method 2, start with S to BSA, inside S, use S to ASB, make S empty, once again using that exponent symbol resulting in AB, combine B plus A equals AB. Well, why is this ambiguous? We derive the same string AB using two different paths. That means we can draw two different parse trees for AB. This confirms that the grammar is ambiguous. And as you can see, there is an example going over each derivation. So as we see in method 1, as explained earlier, and then method 2, we can see the difference in the two different parse trees. So the infix to postfix conversions. I'm going to be demonstrating how to convert the infix expression, the kind we normally use in math, into postfix, which is easier for computers to evaluate. My example is 3 plus 4 times 2 minus 1 in parentheses to the second power. All right, this expression uses four operators: the plus sign, the multiplication sign, the minus sign, and the exponent symbol. It does have different precedence levels. It includes parentheses and can't be evaluated left to right due to order of operations. So to convert it, numbers go straight to the output. Operators go on a stack. If a new operator has higher precedence, it stays. If not, we pop from the stack first. Parentheses help group operations. Everything inside them is handled first. When we see a closed parentheses, we pop until we hit the matching uh, open parentheses. So when we see a right parenthesis, we pop until we hit the matching left parentheses. At the end, we pop any remaining operators. Step by step, this expression becomes 3, 4, 2, 1 minus 2, exponent symbol, multiplication, and then multiplication symbol, then plus sign symbol. As you can see here, this is the postfix form. No parentheses and operations happen in the correct order automatically. I'm just going to give an opportunity to double check my work. So moving on to bottom up parsing. So I'm explaining bottom up parsing specifically using an LR parsing table. Bottom up parsing works by starting with the input string and reducing it back to the start symbol of the grammar, like reversing the process of building a sentence. All right. We use a stack and an LR parsing table. The table tells us when to shift. Shift meaning move the next input symbol onto the stack, or reduce, replace the top of the stack with a grammar rule. And then we also have our last um, instruction that we give, which is called except, which just means finish parsing when we reach the start symbol. So let's take this example, ID plus ID times ID. Grammar includes rules like E to E plus T to T times F and F to ID. We begin with an empty stack and read ID. The table says shift. When we see something matching a grammar rule like ID, we reduce it to F, then to T, and eventually to E. This continues step by step, using shift tokens, reduce using rules until we finally reach just E on the stack and the input is done. That's when the parser says accept and the input is considered valid. And this is shown in the example as you see here on the table. So bottom-up parsing is powerful and used in many compilers like those for, Python or Java. And this is exactly why it's a universal tool and it's a lot more common. Just giving the opportunity to look over my work. And that concludes my presentation. Feel free to comment for any questions. Thank you.